trusted research environments have emerged as a solution to this problem. So trusted research environments are computational environments with technical but also policy controls, which help to make sure that sensitive data is used in a secure, responsible way, whilst enabling researchers to use that data. And some research requires a lot of computational power, and that's where high-performance computing, HPC, comes into the picture. So HPC systems are focused on performing large amounts of computational operations in a very short amount of time, and they did this through specialist hardware and such as accelerators, very fast CPUs, but also fast networking interconnects and fast storage, parallel storage. So we have all the pieces. We've got theories, we've got some sensitive data, and we've got HPC. So, like, what's missing? What's the problem? And essentially comes down to trusted research environments are not high-performance computing systems. So in a trusted research environment, security is always your top priority, and income second. They generally, as it's not necessarily always, but generally will lack the kind of hardware that you would see in HPC systems. Very often they're deployed to the cloud, which has a lot of really great advantages, like you can define the policy and infrastructure in code. That's very nice. However, cloud cost of computing can get quite high, especially if you want to scale up and use lots of high-performance hardware. If a theory is on premises, that doesn't necessarily make it easier. Buying more hardware and putting it in a room requires a lot of space, requires a lot of power, and a huge sort of capital investment in buying that hardware in the first place. And they can be a little inflexible. Theories are often designed for a specific group, specific domain, just the tools they need. Some of this comes from the focus on security, sort of give people just what they require and else, and that kind of inflexibility can make it difficult to use. On the other hand, HPC systems are not trusted research environments. They're designed for performance first and everything else second. They are shared systems, and that's a really good thing, because that means instead of everyone having to buy their own little high-performance system, you have big shared resources like the Tier 2 national resources we have in the UK, and by sharing that, we keep the utilization up, we get good value for the investment in those systems. However, that also means there are lots of users using the systems, there are lots of users sharing them. Not all those people will have the sort of training and knowledge that you might want in someone who's got access to sensitive data, and it does leave the possibility for sort of attacks on jobs that are sharing nodes. There are also, I think, critically, very few controls on data going in and out of HPC, and again, that's by design. The users of HPC want them to be able to get their data, their coding really easily, compile their code, run a job, and get the results out, which is fantastic for fast research, but completely not appropriate for trusted research, where you really want to be careful about what data you're releasing and if you're merging any data sets, and also just sort of what work is going on, what people are doing with that. So what we're doing in Bridge, we're building a ready-to-use such compliance theory that can be deployed to AIRR, and hopefully that means other HPC systems, other computers as well. We're building Bridge on top of Kubernetes, because that's a sort of first-class offering on both the AIRR systems, and hopefully that's a nice, fairly standard sort of base to move Bridge between different systems. So probably the most important part of this is we want to be able to use one of these AIRR systems for research of sensitive data. That means we need some sort of agreement from the infrastructure providers that we can use their system for that. And that can be quite tricky. We need to get that agreement. The approach we've taken is that our aim is to extend the governance boundary of an existing TRE to cover a portion, sort of carve out a portion of the air system and say this is now under the governance of the existing TRE, and we'll sort of secure that boundary. And that's how we're able to do this work. All of the information governance remains and responsibility remains with the existing TRE. And this secure passing system that we carve out, we call the TRE tenancy. So in more detail, the breakdown of responsibility looks like this. This group called the TRE operator. So it's people in charge of this existing TRE. They retain all the governance responsibility. So they manage who has access to the TRE, what data goes in, data sets get merged, the data processing that's going on and what comes out. They're also in charge of deploying and maintaining this bridge deployment on the infrastructure. The infrastructure provider, on the other hand, is responsible for creating this tenancy, so securing the boundary around it and making sure that what's in it is a sort of bridge-compatible Kubernetes, so that we can deploy a bridge in there and we get GPU pass-through and we're able to use all the high-performance features. And these things combined mean that the TRE researchers can just focus on conducting research. So the high-level get to the architecture is like this. So there are secure tunnels between an existing TRE and a TRE tenancy on air. So after the infrastructure providers deploy that tenancy, the TRE operators are able to connect and just use the standard Kube API to deploy all the bridge stuff. TRE researchers then have their own security and they're able to dispatch jobs to the system and get the results back. So critically, important thing here is because this bridge deployment is, as far as governance is concerned, part of the existing TRE, we're very happy to send data over and receive the results immediately back. We don't have to classify that data or go through a process to make sure it's ready to release. It's just going back to a TRE where we've already agreed it's fine for this data to be in, it's fine to conduct this work. In more detail, the current implementation looks like this. So users, there are APIs exposed for the TRE researchers. They submit a job through that API specifically saying, I want to run this calculation with this container image on this data. Argo Workflows takes that job specification and will launch containers in a isolated namespace to run that. That it will be able to get container images from a Harbor repository, container repository, which is Harbor, which is inside the bridge, and we have storage, both S3 compatible object storage through MinIO and access to block-like storage on the host itself. And there are a few other services which the users don't need to touch, but we'll configure the network policy and the reverse proxy and things. So we're hoping that there's a number of advantages to the sort of job dispatch model. Hopefully, well, the APIs that the users interact with should be fairly immutable, independent of what's going on inside the cluster. So whether it's Argo, whether it's something else, the researchers don't really need to worry about that. They have to worry about writing their jobs back and submitting it. So we're sort of protecting the researchers from having to know, they don't have to know about Kubernetes, they don't have to know about a lot of the details of what's going on inside. It also hopefully promotes some best practice and reproducible research working in that. Users will have to devise a job spec and submit it and get it back, and they can iterate on that, and there will be there's a much better audit of the research that's been done. On the other hand, there are some sort of downsides. So if someone wants to do a lot of Poking around in the data, sort of manual inspection, very quick iterative work, it might not be ideal for that. And if people really want a sort of graphical interface, a desktop, a notebook, it also doesn't provide that. But for the theory, I haven't really spoken about how it's secured, and we have a kind of two-pronged approach to this. So inside the Kubernetes cluster itself, role-based access control means that the service account through which users submit jobs have very, very few privileges. They're able to launch containers, but importantly, they're not able to modify what's deployed in Kubernetes at all. Pod security standards mean that the processes which the researchers launch have no permissions over the host system apart from being able to use the accelerators on that host. So it's not possible to trivially say, I want to run a container as root, I want to mount the host file system or get access to the host network. Network policies ensure that only intended traffic is allowed, everything else is blocked. And all the data on volumes is encrypted by keys which the TRE operators are the people deploying for control, not the infrastructure providers. So that data is secure items, even in the event of a data being stolen or someone getting root access on the host system. It still wouldn't give you those keys, you wouldn't be able to read the data. On the other side, on the host, they're providing this isolated tenancy, which means that even if you did manage to break out of your container and compromise the host, you're still sort of in an isolated box. There's still not a good way to get out or for data to be leaked. And we had these secure, sort of verified connections between the TRE and Fridge to make sure that only the intended site is able to connect. The tenancy, in a bit more concrete detail, still fairly high level and generic. This is our plan. So the Kubernetes cluster in which Fridge is deployed is in a completely isolated network with no outbound access. So again, if you manage to compromise the sort of virtual machines which host the cluster, you've still got no easy way out. The inbound access from the existing TRE, so you've got these jump boxes inside existing TRE's networks and proxies on the AIRR system. And it's just simply in SSH tunnel, which is nice because that's very common, well supported, secure. And as far as the users are concerned, what they're really doing is just interacting with an API inside the network of their TRE, but in the background, this is all being dispatched and user. So a challenge, a bit of what we need to do is to take this sort of slightly abstract sketch and make it into real implementations on each of the AIRR systems. Those are likely to be a bit different. If you want to run Fridge on a third system, again, you might have to think about how are you going to take this kind of abstract concept of the tenancy and implement it in practice. But we're quite hopeful that through using fairly generic components, we're just talking about networks, virtual machines, public IP addresses, any sort of cloud system, private public cloud has those tools. So it shouldn't be too difficult to implement in other systems or even on bare metal. So where have we gotten to? We made quite a lot of progress on the sort of high level things. So this shared responsibility model we have refined. We've outlined what the TRE tenancy is in this high level, what the requirements are. We have deployed a sort of minimal viable product on Azure, so we're able to put data in, run jobs, get results back, and we've made a sort of first, not the sort of super user-friendly, but a completely sufficient API for running jobs which in the future we could expand upon, making CLI apps, web apps, however is most convenient for users to interact. Still in progress, figuring out the equivalent API for data to get data in now, including the container images in the container repository, and the governance work to here's an example of the kind of governance agreement you would need between the existing TRE and the infrastructure provider in order to run a system like this. On the air systems, so Dawn and Isabard, in terms of deployment, Dawn was a bit closer to quite high. At least we had sort of more access to it, so we've done a bit more work on that side. But in both cases, we can get Kubernetes, we can pass through the GPUs and use them side processes running Kubernetes. Dawn, which has a very nice self-service sort of cloud interface, we've deployed sort of development of Bridge, been playing that there. In both places, we're now focusing on refining this TRE tenancy concept and having implementations, so real working implementations on both systems, and we're considering the best options for how to go about encrypting the data in both places. We're also making some broad connections, so I think in a way that's pleased me a lot, doing this work on saying, hey, we're going to give you a way to take your sensitive data and get us to run calculations on it on very powerful HPC systems. People really like that idea. We've had people sort of reaching out to us, asking what's going on and if they can be involved when it will be ready. So some highlights there. We spoke to the NHS SD network on how we might be able to augment their subnational SDEs with Bridge so that they'll be able to use HPC resources in their work. The National Institute for Health and Care Research has asked about how Bridge might be accessible, might be used by their, I think it's 20 biomedical research centres across the UK. We had a really great sort of high-level conversation with UK Biobank about whether Bridge might be an option for some of their more sensitive data sets. So I think particularly GP data and genome sequence data. So where they might not be comfortable giving access through the routes which they already do. And also had a really interesting conversation with STSC about whether Bridge could be something which is deployed or offered on the Jasmine Research Cloud, so that could be useful for sensitive data. And we've also had interest from some sort of individual projects, some significant projects, interested in whether Bridge is something they could use to sort of bring that AI/ML sort of high-performance power to their work. We've learned a lot of lessons on the way. So multi-policy governance is always difficult. Data sharing agreements can really sort of kill a project, sort of stop you at the first hurdle. And our approach to this has basically been to avoid that. We're not doing a data sharing agreement between the infrastructure provider and the existing TRE. We're saying we don't need one because of this tendency. That's something we have to test, but I think we're quite confident and sort of agree on both sides. The TRE operators don't really want to go through a issue agreement. The infrastructure providers don't really want to be worried about having a responsibility for sensitive data. High-performance computing is changing. It's not just this scheduler model now where you have to take in and submit a job. In particular, Dawn, we've seen this model where you have portal. It's very much like public cloud, but it's sort of by HPC. You've got one-click apps, and you can even access the OpenStack APIs to deploy quite complex things. Kubernetes, our hope was, this is a common base. Kubernetes is Kubernetes, so if you can deploy on one Kubernetes cluster, deploy on another. That's not quite true. There are important differences between implementations which you need to worry about. It is still a lot easier. So it's a much better starting point to transfer, but it's not quite trivial. And yes, not an original observation, but don't reinvent the wheel. We haven't really developed much new code, new software. We're mainly leveraging existing mature open source, active open source projects. And yeah, that's definitely the sensible way to go. That's saved us a lot of time, and it's projects have many more contributors, are much better than we could have written from scratch anyway. Also, I think probably not original observations, but there are some really quite tricky conversations and decisions to be made in Fridge, so particularly surrounding the governance and what this tenancy looks like. And I think from the beginning we knew those sound like the really important things. If we don't solve those, we can't solve the problem. And that's been true. They have been the most difficult, and they're still ongoing. And I think we've made good progress. But yeah, perhaps something we learned is we could have really focused in on those right from the beginning and ignored everything else for a bit, and maybe that would have helped. So don't be scared of difficult questions, but meet them and have difficult conversations. So where we're going next, that's supposed to be a heart, but it hasn't. Something that's really important is that we don't just make this and say, here it is, it's fine, use it. We want to run a real example. So using sensitive data, it's towards building a cardiac digital twin of a heart. And we think it's really important that we do that so that we can actually prove we have solved this governance problem. We are able to do this. We are able to delegate governance and use AIRR in this way. Yes, we're sort of putting our money where our mouth is and trying to prove that we can do that. There are some unique challenges with scaling to many nodes. So obviously using HPC, using one node is nice, but these systems are massive and scalable, and we want to take advantage of that. There are some challenges around how to secure this across many nodes. Get to address that. And confidential computing, which I'll go a bit about now. So one of the limitations of Fridge is that it requires a lot of trust in the infrastructure provider. So while data is in memory, someone could potentially still read that. So it's requires this high level of trust. But what about environments where you don't have that much trust, or you don't have the time to set up your tenancy? So confidential computing could be a solution to that with the trusted execution environments, which is sort of like the missing link in encryption. So we know how to encrypt data, what's at rest, what's in transit. With contextual computing technology, we can make sure that data is encrypted while in memory, so it's unreadable to processes on the same host. So yes, thanks everyone for listening. That's like the development theme at the Turing at Bristol, at Cambridge, at UCL, dedicated to historically the program and discovery in a different way. You made those excellent illustrations. Yeah, if you're interested, get in touch. Thanks.
That was awesome. We'll do one, two programs in this so what is needed to bring this Warwick up to allowing computers to run their own?
Yeah, so I think, like I said, the bits which are sort of tricky in adapting it, you've got to figure out how to get this idea of the tenancy and how you're securing the storage, and make sure you've got a real concrete implementation of that for your own system. That seems very workable, but with the trustee work that we're looking at, that should make it even easier, because you'll be less worried about other people using the system that sort of your support or compromising the data. But yeah, I think the important bits are finding out how you're going to really in practice implement the dependency and the data encryption.
Thank you very much.